We can move to Viviane Pierrard. She will present the 3D dynamic kinetic model of the Plasmasphere.
Are you going to reshare the screen again?
Yes, because I want to show the simulation as well after the PowerPoint. Are you ready to share? Yeah. The entire screen?
Yeah, it's better. Click on it.
This one?
Yeah. Okay, sure.
Okay, so I will present you now the three-dimensional dynamic model of the Plasmasphere, BPIM, this meaning Belgian Plasmasphere Ionosphere model, that is available on the PITHIA platform and also on the virtual Space Weather Center, modeling center that and Euphoria chain that Kinetic just presented. So what does this model provide? This first, this simulations like that, as shown here. This, especially this the plasma pulse location. This corresponds to the black circles here. That's the limit of the Plasmasphere. This shown here in the equatorial plane and in the meridian plane. Then it provides also the density inside the Plasmasphere and also outside the Plasmasphere, just in the region called the plasma trough. And this has been recently improved, as I will explain a little bit later. Does it provide also the temperature of the particles? That's not especially available on the PITHIA and the Euphoria website, but it's available as well as the composition, for instance, not only the number density of electrons, but also protons and helium ions, for instance. The model is also coupled with the ionosphere. And for this, we use the international reference ionosphere developed by PITHIA. I will explain also a little bit later. Its advantage is that it's dynamic, so it reproduces the formation of the plume, as I explained. This, when the activity increases, you have a formation of this kind of plume. Thus, it's a model that is semi-empirical and physics-based. It's physics-based because the plasma pulse position is obtained by the mechanism of interchange instability, as I explained this morning. Also, the motion of the particles are taken into account, but it's also semi-empirical because, for instance, the convection electric field is based on the observations of different satellites. So, so here you have several references because the model was first developed in 2008. And the coupling with the ionosphere is described in this paper of 2011. And then recently we made some improvements for the model that are explained in this last paper. So the plasma pulse is really what is the most dynamic in the model. Thus, it is formed in the equatorial plane, in the post-midnight sector, as I explained this morning, due to the mechanism of interchange instability. So to produce that with the model, we need to first have an input, and the input is the date. Thus, you can choose the date that you want to reproduce, and then the model, well, the model needs the KP index that is observed during that day and during the previous 24 hours. Just when you enter the date, it provides that. And from this position, from this KP index. Thus we launch plasma elements, and these plasma elements, by the mechanism of interchangeability, will come to the position of the plasma pose. And thus, as I have explained this morning, this when the activity is high, the plasma pose goes closer to the Earth, and we take into account also just the co-rotation. The model is also available on the Space Situational Awareness website of ESA, just the European Space Agency, in the section Space Radiation. On this section, it's a little bit different. The model is provided in real time. And you can also enter a given date, but it has to be after 2017, because that's when the model was implemented in the ESA website. And this is an example of what you can obtain. This model at that time was in Fortran in IDL. That's why the color code is a little bit different. But now it has been translated in Python, and that's why it appears with this color code in the most recent version. So here you can see, for instance, the number density well, a few days ago, and the electron density. On this website, you can also obtain the temperature. This temperature is always, of course, larger in the day side. This in the night side, shown by the black circle here. This you have a lower temperature, given by the blue region here. The model presently has been improved in comparison to that, because mainly because it has been coupled with the ionosphere. Thus, for that, we use the International Reference Ionosphere model developed by Vilica. We use the version of 2016. And note that this model is also available on the PITHIA website, but the version of 2001, I think. But anyway, thus we use these values of number density and temperatures up to 600 kilometers, because in general, that's what that corresponds very well. And above that, we obtain this, we couple with the Plasmasphere, and then we can obtain this, we use as boundary conditions, and this we can have a different result from what is given from IRI above 600 kilometers. This model, IRI, is also given by the date, and it's an empirical model. It's based on radar observations and satellite observations, so that you can have the density and the temperature of the different particles in the ionosphere at any time. So, because the particles circulate along the magnetic field lines, we can obtain just the number density at all different distances inside the Plasmasphere. There are different websites where you can find this version of the model. It's the PITHIA website, the Virtual Space Weather Modeling Center that Nathan just shown. And in fact, yes, it's just the coupling, this link that is provided on the PITHIA. And there was also a version on the Safe Space project, because this was used to predict the geomagnetic activity indices, and then also the Plasmasphere, how the Plasmasphere would be. Because that's a more forecasting. Here on on the website of ESA, it's more no casting, and on PITHIA it's that you can enter any date that you want in the past. So the model reproduces also the plumes. Thus, these tails forming when the activity is high, thus mainly forming in the afternoon sector and then rotating with the Earth. Thus, you can have such a plume that remains several days, but in fact, it appears only if the geomagnetic activity remains high or is high again. Then the plume remains, but otherwise it disappears after 24 hours when the new plasma pose is formed just in this post-midnight sector. Thus, what you can have, there's not only this nice movie and nice simulations, you obtain also the files with the data. Thus, what is provided is the density of electrons in cubic, in a number of per cubic centimeter, as a function of the radial distance in Earth's radii, the magnetic local time in hour, this magnetic local time day side or night side, so on, the latitude in geomagnetic coordinates, because we are here in geomagnetic coordinates. This, you can see here there's some profiles, for instance, for the number density here. This, at low altitude, this we have the number density obtained by IRI, this, the ionosphere model. Just here for the day for the black side and the day side for the black line and the green for the night. Then you have the coupling with the magnetosphere at larger distances. Then the plasma pose that is different depending on the magnetic local time. This day side and night side, it's different. There's a sharp decrease of the number density. And then here, the number density in the plasma trough, thus above the plasma pose. That's for the number density. Thus you can have it on in each direction. Here it's in the equatorial plane. And here you have the temperature. This again, the temperature is, we take the temperature as obtained by the ionosphere model at low altitude. The temperature of electrons is always higher than the temperature of the protons and other ions. And of course, it's also higher day side than in the night side, of course. And then it's proposed to obtain the temperature in the plasmasphere. It's slightly increasing, reaching several thousand Kelvin. So in the model, we have tried different convection electric fields to see what it gave us. Here you can see an example with a Wallenstern convection electric field. This, you remember this morning, this you have the co-rotation electric field that dominates at low distance, this because the plasma is in co-rotation, and at larger distance you have this convection due to the solar wind effect. This, there were different models depending on the observation of different spacecraft of observations. This Wallenstern gives, for this specific storm of April 2002, for instance, this it gives, well, the plume is reproduced for all the different electric fields, as you can see. This, you have a KP that increased up to 6. It's not a very big storm, but it creates a plume in each case. This E5D is shown here and Weimar here. And well, in fact, by comparison, we obtained that the E5D is the model giving the best the plasma pose position that is the closest to what is observed. This we made in comparison with the satellite image, just that gave the plasma pose position with global views, as I explained this morning. And well, the other electric fields are stronger and then give a plasma pose position that is a little bit too close to the Earth when the activity is high. For the magnetic field, we use M2, that is a magnetic field close to a dipole, but slightly anisotropic, just taking into account the tilt with the geographic, with the axis of rotation, and also the anomaly above South Atlantic. The convection model is dependent on KP. That's really what is different with the date. Thus, here you can see an example also again of comparison we made to validate the model, to compare with observations. Thus here we have an example of a substorm. Thus a small increase of KP up to 5. And on 9 June 2001, thus we are here before this increase, then the plasmasphere is quite extended up to 4 Earth radii. And after the substorm, this 1 day later, typically, we have this formation of a plume with the model here in the afternoon sector, and a shoulder due to the sharp decrease of KP after the storm. Thus you have the plasma pose that goes further, and you have this refilling in this region here. Thus we have compared with image, this observation of the satellite image that provides observation from 2000 to 2006. The best observations are in 2000 and 2001. This when the spacecraft is above the North Pole, thus we have no observation all the time, only several, 1 or 2 times per day. And well, at that time, thus we obtain indeed a plasmasphere quite extended and almost circular, while after the storm, we obtain indeed this, well, it is observed with this spacecraft that there is a plume formed here correctly with the Earth, and even the shoulder here is reproduced, even if it's a little bit not exactly at the same magnetic local time with the model. Thus, we made also many comparisons with other observations from cluster CRESS, Themis, Kaguya, and many others. And generally, the model gives very good comparison with, in average, because it can be different from one day to the others. This inside the plasmasphere and for the plasma pose position. But for the plasma trough, this above the plasma pose, then the model was not very good because we didn't care so much that part at the beginning. This in the previous version, this the number density in this plasma trough was obtained by observations of ISEE2 measurements, this given by Carpenter and Anderson in 1992, and that were extrapolated to all magnetic local time. But because here you can see what was predicted by the model and what is obtained by the Van Allen probes, the satellites just launched in 2012 by NASA that crosses the plasmasphere and the radiation belt. And you can see that the density in the plasma trough are much the densities are higher than what is predicted by the model. So we have now improved this part of the plasma trough by using the new observation of Van Allen probes. But what is also important to note is that you can have differences in the model also due to the KP index, because as I mentioned, the input of the model is simply the date. And for the dates, you can have the KP forecast, for instance, given by NOAA. And you have the KP definitive that you can find on the Potsdam, for instance. And you can see that sometimes the prediction of the KP or even what is observed in real time can be a little bit different from what is selected finally as a definitive KP. Thus, to improve this part of the plasma trough, the low density above the plasmasphere, that were too small with the model of Carpenter and Anderson, we have used the new Van Allen probes, or RBSP, this the new name of the satellite, observations, this made by the instrument MPhysis that gave this the number density in this region as well. And we use the same fit function as was used by Carpenter and Anderson, but using new fits, thus finding this A, B, and C indices to reproduce the observations. So the observations are given here. This at the top here you have when the activity is small, this KP lower than 3, and at the bottom when the activity is higher than 3. For different magnetic local time, this here on the left from 0 to 6 magnetic local time, here from 6 to 12, 12 to 18, and 18 to midnight. And well, the Carpenter and Anderson previous model, this is given by the red line, and you can see that it's especially when the activity was low that well the model underestimates what is really observed in all MLT sector, while for the higher activity, the previous model, this again given by the red line, was not so bad, except in a high magnetic local time. Thus the new fits, thus are shown by the black line, and well, you can see that it reproduces better the observations of the Van Allen probes in this region, where the Denver density is very, very low. It's less than 10, well, often between 1 and 100 maximum particles per cubic centimeter. But it's important because, for instance, we needed better modelization in this region to analyze the chorus waves that are generated in this region, and this with Onera in France. We calculated the diffusion coefficient associated to this chorus wave using our model to reproduce the observations of the Van Allen probes for these waves and the radiation belts. So other comparisons that we have made, this with cluster, I mentioned already this morning also, Themis, double star. There are many observations that were used. This here, for instance, for Themis, this we made statistical study for the position of the plasma poles. This we have more than 6,000 observations of plasma pose by TEMIS here. That's the green points shown here for low activity. This here, it's the AP index that has been shown. It's a little bit like AP, but not limited to 0 to 9. There's low activity at the top and high activity at the bottom. This, if we calculate the mean TEMIS plasma pose obtained, we obtained this red circle that is clearly closer to the Earth when the activity is high than when the activity is low. This, if we compare with our model, we obtain also this plasma pose that is closer to the Earth when the activity is high. But you can see that the dispersion is less high. This, in fact, yes, statistically, in average, the model gives good results, but you can have some cases when the plasma pose is not completely well reproduced. But yes, here on the right, we compare this, the mean TEMIS plasma pose this in red with the mean model in blue, and you can see that this, in average, it gives very good results. This again, here you have observation of CRES in blue, observation of the plasma pose position in Earth's radii here as a function of the KP index maximum observed during the previous 24 hours. Thus, the best fit is shown for the CRES data is shown by the pink line here. And we compared with Van Allen probe's new observations of sand in black, and with the results of the model shown here in red. With the model, it's not especially a line, it can be different, but again, you have clearly this plasma pose going closer to the Earth, but with some dispersion higher in the observations than in the model. That is an average model. This here you have again a comparison of what is observed with Van Allen probes. This at the top you have in black the plasma pose position measured by EMPhysys, and the color scale corresponds to the outer radiation belt, this the flux of particles at 2.2 million electron volts. As you can see, again, as I explained this morning, when there is a storm, this that you can see here by a DST inverted peak here, for instance. This is the DST index. This when this DST has an inverted peak, this you have a storm, and the plasma pose goes closer to the Earth, and you have this injection of plasma closer to the Earth. And here, the second plot here show the plasma pose obtained with the model. That's the black dotted line, and observations of the radiation belts made by our instrument, the Energetic Particle Telescope. That has a completely different orbit, a low Earth orbit, but that show also the same injections, and especially sometimes injection in the inner belt. This is the case only for energy lower than typically 1.1 million electron volts. And here you have really the comparison of the observations of Van Allen probes in black with the result of the model in red. And well, you can see that the plasma pose is quite well reproduced in general. Also on the PITHIA, that's for the model. Also, our instrument or institute provides other data about the Plasmasphere on the PITHIA website. This you will find, especially the cluster observations made by the instrument WHISPER. This corresponds to a spectrogram like that, where the clear blue line corresponds to the frequency of the plasma. Thus, the sharp decrease here corresponds to the plasma pose. Here, the plasma pose. Obtained this with the 4 different spacecraft that have an orbit very close, but that can show the motion of the plasma pose position, for instance. Just because this frequency of the plasma, you can transform it in number density along the orbit of the spacecraft. And so that's what we can obtain this with plasma, with this cluster observations, this number density along the satellite orbit. Also, in the future, not yet available on the website, but to be provided, this observations of our ground-based very low frequency magnetic antenna that detect the Whistler waves, as I mentioned this morning. Just you remember that when there are lightnings, this you have a creation of these Whistlers, and when they cross the geomagnetic equator along the magnetic lines, you can determine the density inside the plasmasphere. Thus, we have 2 antennas like this, one in Belgium, in the site of Louvain. This is located at 50 degrees of latitude in the North Hemisphere. And we have also one in Antarctica at the Princess Elizabeth Station. It's in the north of Antarctica. It's located at 65 degrees in the South Hemisphere, and it's important because you need to have still a close magnetic field line so that it's useful. And then here you can see the Whistlers that are detected. The antennas detect also the chorus waves. This is what is observed in the Antarctica station, and this is what is observed in Belgium. As you can see that the signal is much clearer in Antarctica, but also fainter. And this, we're using the Worldwide Lightning Location Network to find the lightnings. Creating this Whistler, we are able to determine some information about the plasmasphere density. So before I show you how you can reach all this information on the PITHIA website, PITHIA platform, exactly, I summarize the important information about the plasmasphere. This, the model is available on the PITHIA website via via the virtual space weather modeling center. This and it's also available in real time in the on the Space Situational Awareness website of ESA in the section Space Radiations, where you can find also the EPT observations that I have shown to you. These observations, our instruments for radiation belts, on the satellite probably. Thus, as an input, you have just to enter a date, and then the model determines the KP index that was observed during this period and 24 hours before to determine the plasma pose position and also the coupling with the ionospheric model up to 600 kilometers, and then it calculates the number density inside and outside the plasmasphere. This outside the plasmasphere, it's the trough, and in the new version, it will be with the observations of, based on the observations of the Van Allen probes data. This it provides not only the density, but the temperature is also available on request then, because on the PITHIA website you have only the number density. The plasma pulse is obtained by interchange instability. You have not only this animated Plasmasphere simulations in the equatorial and meridian plane, but also data files with the number density as a function of the different coordinates. The model is semi-empirical and dependent on KP. And yes, it's not implemented in the automatic version, but the plasmaspheric wind and the refilling after an event can also be obtained, but then you need more than 24 hours, for instance, because this process takes more time. Takes more time than 1 day. So, for instance, as I mentioned, the plasmaspheric wind appears only if you have long time period of low activity. So you need to have not only 24 hours before, but much more important time interval to analyze if you want to reproduce them. So here you have the main recent publications about the model and the comparison with the observations to validate the model. So now I will try to show you how you can obtain the model in on the PITHIA website. Thus, you have here well, the website with the different models and data. Thus, you can click on data collection, and then you can see here the model is given here. Thus, you just click on it, and you have the informations about the model. This is a summary of what I have explained. This the input and the assumptions that are made in the model and so on. Thus, you have the different properties. You can click on these different things if you want. But, well, what is important is here this link with the space situational awareness of VISA. This here for the virtual center, this Euphoria website. If you Thus, you have to register and to log in. As you can see here, if you go there in space radiation, you will find the model in real time. But here I show you how to run it on the virtual center. Thus, you can put here new run. And here you have different chains, as Jonathan explained. This, but what you want is the BIP model. So you click here on the selection, and you click all the chain corresponding to the BIP model. This is the Plasmasphere model. This you have different possible chain. But if you want the best prediction, you need to take the simplest one, just the one that takes the KP index as it is observed, and then determine how the plasmasphere is then predicted. If you use Euphoria, then you will obtain a prediction based on the predicted KP, for instance. This is the model that you have to choose, especially if you want to enter a date in the past. Yes, you go there and you enter the date that you want to simulate. Thus, you can choose any date that you want, and then you put start the run, and you will have the run that starts. And it takes typically for 1 day, it takes 15 minutes before you obtain the results. So, because you want to see what it gives, you go to history, because I have already made some simulations. You go, for instance, here. Not this one. This you can see here previous simulations that were made. Just let's take, for instance, this one. You go to results to see what you can obtain. Thus, you have different files like this. Thus, every hour, you have this at 0, this universal time, 1, 2, 3, 4, and up to 24. Thus, you have files with the data. Thus, you can download one of them, for instance, and you obtain here this as a function of the the data here, this the radial distance in Earth's radii, the magnetic local time in Earth, and the density, thus here in the equatorial plane, thus obtained with the simulation. That's for every hour, and then at the bottom you have the movie. Oops. This we go to the bottom, and you have, for instance, the simulation for this date. Let's open it, and you can see here the simulation for this specific date. This, for instance, here it was 9 October 2015. And so that's how you can run and obtain the results of the model. So we can go, for instance, in space radiation here to try to obtain the model in real time. Yes, you go, for instance, here on Space Weather Services of BIRA, and the Plasmasphere model, this in the old version, this it's an older version, and you can see here for today what is obtained with the model. This here for the number density of electrons, and here for the temperature of the electrons. Okay, so let's come back maybe to the oops. Yes, no, yes, let's come back to this. This and especially to the PITHIA website. Up, I come back here. Let's see now that I don't want especially the model, but I want to find everything about the plasmasphere. Then I go to Earth. Here, it's a region of the inner magnetosphere. So I click on magnetosphere, plasmasphere, inner plasmasphere. And then I go to search. And then I have the different collections that concern the plasmasphere. This, again, you find the plasmasphere model, but you have also the cluster observations here that I mentioned. So you can click on this. Then again, you have all the explanation of cluster, the satellite, and so on. If you want to access the data, you go there. This is again the ESA website. This you have to register if you want to have access to the data again. Okay. And then this you have, in fact, not only that you have all the cluster observations, not only the instrument whisper, but we are interested, for instance, to have some graphs, and especially to have cluster, yes, cluster. Thus, we want, for instance, the instrument whisper, because that is what I mentioned. Thus, you have the 4 spacecraft. Just let's take the 4 spacecraft, electron density here, or the wave spectrum, but we want the density of electrons. We can enter a date a little bit later after the launch, otherwise we will not have anything interesting. We click on plot, and then you can have, for instance, here, for the different spacecraft, just the number density of electrons along the orbit. Okay, this that's what I wanted to show you, and yeah, I stop here so that you can be free a little bit earlier.
Thank you, Viviane. There is any question? No question for Viviane?
I know that there are not
We
so
have
many
plenty of
people
time.
working with Plasmasphere, but you can see that there are links also with the ionosphere because we use the model. And what is important for maybe for people working with the ionosphere is that the reference ionosphere model of Bilica, you see it is good at low altitude, just where you have the different layers, D, E, F1 and F2, but at higher altitude, even when it provides this, it provides density up to 1,000 or 2,000 kilometers. This one is not really correct. It's too high in comparison to what is really obtained with the Plasmasphere. Like if all the density of the column has been made up to 2,000 kilometers. So
Which altitude it's reliable?
Typically 600 kilometers, 800 kilometers is still okay. But if you want something more reliable above, it's better than to use the Plasmasphere model.
Thank you, Viviane. Any other question? Let's thank Viviane again.
Thank you.
Thank you.